Hello and welcome to this lecture. In this lecture, we're going to study the most important property of a sequence, which is the limit of the sequence. Okay, so we saw these sequences basically for every integer you define a real number as its, that's the sequence corresponding value of the sequence corresponding to it, and then you look at this whole sequence, and there are different types of sequences, and they're showing different types of behavior. And sometimes it looks like the sequence can be really powerful. You define it with a recursion and it seems to have some very interesting properties. Okay, most of the properties of sequences which are useful in computation, function evaluation, continuity, differentiation, all of that has got to do with the limit of the sequence. Does the sequence have a limit? What is the meaning of a limit of a sequence, limiting value of a sequence? If the sequence does not have a limit also, it's interesting, but still it's a little bit more interesting when the sequence has a limit. Okay, so the limit is very crucial. So we're going to define it rigorously and see a whole bunch of examples, motivations for why that goes. Okay, so let me start with a motivation. Okay, here is a plot of two sequences, a stem plot of two sequences for a large value of n. I've gone up to 100. Okay, 100 may not be too large, but anyway, large enough. Okay, so you see in both cases, something is going on, right? So the sequence initially it is doing all sorts of things. It's being high, low, and all over the place. It seems to be sometimes it's above, sometimes it's below. It's going there. But one thing that's happening to the sequence throughout as I increase n is, it seems to be getting close and close to 0, right? This red line that you see here, the 0 line. As you go to larger and larger n, it seems to be approaching 0, right? Same thing is happening to this sequence. It's not approaching 0, it's approaching some 0.5, right? You see here, it just, it's negative even here. At some positive value here, it goes less than this value here, up and down and up and down and up and down. But one thing uniformly that the sequence does, as you go to larger and larger n, it is getting closer and closer to this particular value, this red line value, somewhere around 0.5, right? So that's what is happening. Okay. So this kind of behavior, right? As n increases, the sequence is becoming closer and closer to one particular value, right? This is sort of interesting to capture. Even in the root 2 sequence, we saw this was sort of happening, no? And that limiting value seems to have some powerful properties which you can otherwise not have. So it's interesting to see what this approaching means. Okay. So loosely we can say graphically, it should sort of get there, but that's not good enough. No, we have to be precise. Mathematics is about also being precise. So how do you precisely capture this behavior in a mathematical manner? This manner of, as n becomes larger and larger, my sequence is tending to something. It's capturing. It's getting closer, approaching some particular value. It could be above or below, but its deviation from that value is decreasing and decreasing and decreasing. How do I capture that? Okay, so that is captured by the notion of a limit. Definition of limit is given here. I've sort of given you the technical definition. This is also called the epsilon definition. Okay, we'll see what it means. Okay, a sequence an tends to a limit capital L. Capital L is some value. Okay, if the following is true. Okay, what is that following? Given any epsilon greater than 0, think of epsilon as a small value, 10 power minus 3, 10 power minus 6, like very small value, 0.1, 0.01, 0.001, small value. Given any small value, I can find an integer, capital N epsilon. What does that mean? Usually when I write capital N subscript epsilon, what does that mean? This is an integer and it can depend on epsilon. So if I give epsilon as 0.1, I might give you one integer. If I tell you epsilon is 0.01, I might give you a different integer, okay, larger. But what should be the connection between this n epsilon and an and all that? Okay, this is what it is. For all n greater than n epsilon, so n epsilon is some large number, so epsilon is very small, n epsilon is some large number. For all values of n greater than n epsilon, to the right of n epsilon, what should happen to an? An should be bounded by L plus epsilon on the top and L minus epsilon at the bottom. Okay, so this is the definition of limit. If this is true for every epsilon, then we say that an is tending to L in the limit. It's approaching L in the limit. Okay, it's a very strict definition involving epsilon. If this were true, then we have this notation. Let me just talk about this notation and we'll come back to this definition and see what it means graphically. You will get a better picture as to what is going on here. The notation is very succinct notation, clearly captures this. It says limit as n tending to infinity, that's how you read it, limit as n tends to infinity an equals L. If this were to happen, okay, if a sequence an has this limit L, has a number L which has this powerful property, however small epsilon may be, I can go to a large enough n epsilon so that to the right of that I am within epsilon of L. An is always within epsilon of L, right? That's what this means, okay? So let me graphically capture this for you. I have my an versus n plot and I have my L, okay? Supposing if this L were a limit, what should happen? If I give you epsilon as 0.2, if I say epsilon is 0.2, I have this L line here and then I have a L plus 0.2 on top, L minus 0.2 on below that, okay? That's my like sort of tolerance, right? The error that you can have. You have L, then L plus 0.2 above, L minus 0.2 below. And notice this particular n 0.2, what is this integer n? Some value here, it is some n 0.2, and to the right of n 0.2, all my values of an, all my sequence values an are within L plus 0.2 and L minus 0.2, okay? Okay, I hope you see that. Now, I want to point out this is like a stem plot except that I have removed the stems, okay? So, I have just only shown you the point, whereas if I put the stem here, it is a little bit very distracting. I have only shown you the point, I have removed all the stems just for clarity. I mean, this is just a stem plot. So, you see this, what is this L plus epsilon, L minus epsilon, right? So, to the right of n epsilon, when epsilon is 0.2, all the values of the sequence are within epsilon of L. So, to the right of n 0.2, any an you take, if you do a subtraction from L, you will be within minus epsilon. Okay, it is away from L by within epsilon. It could be on the positive side, could be on the negative side, I don't care, but it should be within epsilon. So, you may pick another epsilon, like for instance, I might pick an epsilon of 0.1. So, if you draw that line L plus 0.1 on top, L minus 0.1 below, you see that somewhere here, okay, it could be here, it could be a little bit further away, it does not matter. There is this capital N 0.3, which is some integer here. To the right of that integer, all my values in the sequences are within the L plus epsilon, L minus epsilon, L plus 0.1 minus 0.1, okay. So, this is the meaning of the definition, and this should happen for every epsilon. Okay, keep that in mind, that is very important. It is not enough if I just do 0.2, no. Any epsilon, any meaning, however small epsilon may be. So, now what is happening here? I will keep decreasing epsilon, decreasing epsilon, decreasing epsilon, decreasing epsilon. Eventually, I will get very close to L, as close to L as I want. But still, what should happen? There should be an n epsilon, beyond which all my rest of the sequence should be within L plus epsilon, L minus epsilon. If that happens, then the limit of this sequence is equal to L. Okay, seems like a very strong requirement, right? So, this requirement really nails down the asymptotic behavior of the sequence an. What happens to an when n becomes very large? Even though it actually takes different values, I can think of it as being capital L itself. So, that is what the limit means. The limit n tends to infinity of an equals L does not mean that an equal to L. Okay, a lot of people, when they look at the limit, think that an itself becomes equal to L. An need not become L. Okay, it can be a little bit away from L, but however, what is the guarantee? I can make it arbitrarily close to L. I can make as close, I can go as close to L as I want, but I can never be equal to L. Okay, maybe that's okay, it's allowed, it's okay. Okay, when I do that, I get some powerful properties for sequences. Instead of restricting to one particular type of number, if I say I can define my limit as some number that is closely associated with the sequence is sort of getting there, then I get really powerful properties. Okay, is it even possible? How do you show a limit like this exists? Graphically, you can show it. Here is the first sequence for which we are going to show limits. Here is the sequence an equals 1 by n, n equals 1, 2, 3, so on. Okay. For this sequence, we are going to show the limit. Okay. So, first thing you start with when you have to do limits is you do the stem plot. Okay, you do the plot, you look at what's happening, right. So, here is the an equals 1 by n plot. I have plotted it up to 100. If you were to look at this plot, it's very, very obvious that the best guess you can make about the limit is 0. Right. So, you see that it's falling, really close to 0. So, if I were to guess the limit of this sequence, I am going to guess 0, isn't it? So, graphically you can be happy, okay, you can say limit is 0, I am happy, but notice one crucial thing. Is an equal to 0? No, an is not equal to 0. Any value of n you take, the value of an is 1 by n, right? It's 1 by 10,000, 1 by 100,000, 1 by 10 power 200. It's never equal to 0, but we always say the limit as n tends to infinity, an is 0. And the limit is defined in a different way, right? It's not the value of an is within 0 eventually, right? That's what it means. Okay. So, how do you prove this limit? You have to actually construct a n epsilon. Okay. So, this is how I am going to construct an n epsilon. I will quickly go through this argument. We will not repeat this argument often. We will find a workaround around it. But anyway, so once you should see this argument. How to find n epsilon given any epsilon greater than 0, right? So, this is what you have to do, right? So, if I have to show that the limit is equal to 0, prove analytically that the limit is 0, I have to show you how to find an n epsilon. Give me an epsilon, I will tell you this is your n epsilon. Go to the right of this, you will be within epsilon of 0. Okay. So, since we are guessing L is 0, we need 1 by n epsilon to be within minus epsilon, right? So, think about this a little bit. Okay. So, what do I want? I want L is 0, right? L is 0, the limit is 0. So, an for n greater than epsilon, n epsilon should be within minus epsilon and epsilon. What do I know about this sequence 1 by n? It is a decreasing sequence. So, if I show that 1 by n epsilon is between minus epsilon and epsilon, that's enough for me. After that, everything else will be done. So, this is the first step in the proof. Think about why that is true. Okay. So, this is enough to show that for all n greater than n epsilon, an will be between minus epsilon to epsilon. Okay. Now, lower bound is trivially true. This minus epsilon, there is nothing to prove here, right? Why? Because 1 by n epsilon is positive. So, there is no problem here. It is greater than 0 itself. For the upper bound, we need 1 by n epsilon to be less than epsilon, which is the same as n epsilon being greater than 1 by epsilon. So, you pick n epsilon as any integer greater than 1 by epsilon, then you will get an n epsilon that is corresponding to this limit. Okay. So, it's a very easy thing. If you think about it, I mean, I am writing it all formally, but it's very, very easy. An is 1 by n. Okay. For any epsilon, I want to be within epsilon of 0. How will I go? I will go to the right of 1 by epsilon, right? Right. So, you have a 1 by epsilon. I pick my n to be greater than so given an epsilon, maybe I should write it on this one, sorry. So, given an epsilon, if I pick n greater than 1 by epsilon, that implies an, which is 1 by n, is less than epsilon. Okay. So, if an is less than epsilon, what does that mean? This is 1 by n less than epsilon. So, for all n greater than 1 by epsilon, an, okay, let me write what this is. For all n greater than 1 by epsilon, an is less than epsilon. Okay, so this is what's important. For all n greater than 1 by epsilon, an is less than epsilon. So, in my plot here, if I am plotting an versus n, this is the first time we are doing it, so we can do it in some detail here. So, if I go to the right of 1 by epsilon, in this an plot, I will be within epsilon. All these points will be within epsilon to the right of 1 by epsilon. Okay. So, it's a very, very simple thing. So, and this is true for every epsilon, right? As you keep increasing epsilon, As keep decreasing epsilon, this 1 by epsilon will keep on increasing, but the moment I go to the right of 1 by epsilon, for all n, I am going to be within epsilon. Okay. So, this proves analytically that the limit is 0. Okay. So, a lot of people get stuck with this proof. They think, what is this? This is such an obvious thing. Why are you worrying about the proof? It's obvious. You're happy, no problem. Okay. But if you want to strictly apply the definition and make only precise deductive steps to get to the proof, this is the analytical way to sort of write it down. I wrote it down very quickly. I wasn't very precise about it. This course is not about teaching you how to write proofs. That you can do later on in life if you're interested, but clearly you can see limit is 0. Okay. So, this property is very important for us, the 1 by n limit being 0. Okay. And we will not go back to this kind of proving epsilon limits all the time. We will develop other methods to find limits. Okay. So, you're happy about that. So, we won't do this proof again. This is just for your own interest. If you want to see, we will develop other methods to quickly find limits, and that we will study as we go along. But let's see a few more examples of these limits, just guessing limits for a few more examples, and then we'll proceed further from here. Okay. So, we have proved at least in one case that this limit is equal to 0. Okay. Okay. So, let's see other examples. Okay. So, here is once again, I am going to start n with 1, 2, 3, etc. I have my natural number sequence 1, 2, 3. For this, the limit as n tends to infinity, there is no limit here, right? It keeps on blowing up, there is no limit. But but what's happening here is it's going to larger and larger values. So, this particular case, people usually denote that the limit is infinity. Limit is plus infinity. It goes on increasing in the positive direction to a very large value. So, such sequences are said to diverge to infinity, diverges to infinity. Okay. So, what is this infinity? I don't want to define infinity and all in this course. You simply think of this as some value that is very, very large and positive, right? So, it keeps on growing. So, we'll call that as infinite. So, this sequence clearly 1, 2, 3 keeps on growing. There is no way in which you can put a limit and say that. So, this will just go off up to infinity. Okay. So, that's the first example here. So, if you look at this minus 1 power n, again it's interesting, minus 1, 1, minus 1, 1, minus 1, 1, there is no limit here. Okay. So, why is there no limit? It goes to minus 1, 1, minus 1, 1, minus 1, 1. I can't put any particular value and say it is going to approach that. No, it's not approaching that. It's always at minus 1, 1, minus 1, 1. Okay. Some people will say, what about my 1? Can the limit not be 1? No, but minus 1 always occurs. However, to the right you go, you will be away by minus 1. It's not epsilon from 1, no. Minus 1 to 1, the distance is 2, always 2. So, you will always have these points that are away. So, a sequence like this has no limit. Okay. Think about the picture. I think maybe the stem plot is a little bit interesting for you. So, look at the stem plot. The stem plot keeps on alternating. It is not diverging to infinity also. It's not going off to some very high value. You can't say it's a divergent sequence infinity. Okay. There is really no limit for this sequence. It keeps going up and down and up and down. That neither diverges. There is no limit. It's bounded. It's not monotonic. There's no limit. Okay. So, that's what happens for this sequence. Notice this sequence 1 by n, we just showed, the first sort of proof that we did in this class. We showed that it is 0. Okay. The limit is 0. If the limit is a finite value, not infinity, but the limit exists and it's a finite value, we say that the sequence is convergent. Okay. So, these definitions are important. If the sequence goes off to plus infinity or goes off to minus infinity, okay, so we will say that the sequence is divergent. If the sequence has a limit, then and the limit is finite, we will say it's convergent, and if it has no limit, it has no limit. Okay. So, here is another interesting sequence, minus 2 power n, minus 2, minus 4, minus 8. This we will say as a limit of minus infinity, just for convenience. It actually diverges, right? It goes off to minus infinity. There is really no limit, but it goes to a very, very large negative value. So, we will say the limit is minus infinity. Okay. So, these are all like just conventions. This plus infinity, minus infinity referring to divergence series just captures the behavior of the sequence, right? So, what we really want, we're studying sequence. I have a sequence, I want to know how it behaves for large n. Okay. It may converge to one particular value, it may have a limit, that's great. It may also diverge to plus infinity. I want to know that, right? So, I will capture it within the same notation to say limit is infinity. It may diverge to minus infinity, that is also important to me. So, minus infinity, though it is not a limit, I sort of introduce it into this notation to make it easy for me to represent the type of sequence. But truly the confusing sequences are those like this for which there is no limit. So, asymptotically there is no limit. What about this guy here? Notice this minus 2 power n, it's going off, it's blowing up, but it's going positive, negative, alternatively it's blowing up, okay. So, this one has no limit. I have to say only none, I can't say plus infinity or minus infinity, right. It is going off higher and higher, but it is not going uniformly to either plus infinity or minus infinity. So, I can't even say it's like that, it's divergent in that way, it's sort of, there is no limit, that is the correct thing to say here, okay. So, you see here all these, okay. So, I hope you saw these examples and you get a feel for how limit works, okay. Limit is the asymptotic value, sort of. If it converges to one particular value according to our epsilon definition in that strict way, it approaches that properly like that, then we say the limit is that particular value, series is convergent. If it goes off to plus infinity, I want to denote that into the same notation. It is not properly according to my definition of limit, but I want to bring it back into this notation to just, make it easy for me to study, classify sequences. So, I will say it diverges to plus infinity. Those are some examples. It may diverge to minus infinity, or it may have none of these behaviors. It's not going to a limit, it's not going to infinity, it's not going to minus infinity. In those cases, I just don't have a good asymptotic property. That's all. Okay, there's no limit. Okay, let's see series. Okay, series where before we go to series, we'll see slightly more complicated sequences defined with recursion. The arithmetic progression, again you can see very easily, if d is positive, it's going to diverge to infinity. If d is negative, it's going to diverge to minus infinity, right. You can see that. That's how arithmetic progressions behave. Geometric progression, the 2 times r power n example that we had, if r is greater than 1, it's going to diverge to infinity, it's going to blow up to plus infinity. If r is between 0 and 1, the geometric progression ends up having a limit of 0. Okay. Again, you can do a proof for this using the epsilon method if you want, but there are other ways to prove it. Maybe we'll prove it later on. So, r power n is going to go to 0 when r is between 0 and 1. Okay, you can plot it, you can check it graphically. When I'm not doing it here, you can check it. The root 2 sequence will go to a limit of root 2. Okay, so this is something really interesting, and this is what makes sequences and their utility for function evaluation. How do you find root 2? You can find root 2 as the limit of a particular sequence of rational numbers, and that root 2 is in fact the limit of this sequence, is something that we need to prove. We have not proved it yet. Graphically, you can show it, but analytically, how do you show that this sequence converges to root 2? Okay. So, this is a challenge. We haven't yet developed such methods. I haven't told you how to do it. It's actually not very hard. It's very easy. We'll see later on how to show, once we know that a certain recursion converges, how to find the value of that recursion, in the limiting value of that recursion. It's quite easy. We will see that. Later on in some other lecture. Okay, let's close this lecture by looking at the series examples. The natural numbers n equals n, and this results in the summation series 1 plus 2 plus so on till n. This diverges to infinity. Okay, so this is quite easy to see. The harmonic series and its the variant 1 by n squared summation are very interesting. So, these are all results that I'm going to state here. We will prove these things later on. Okay, eventually we'll prove these things, I promise you that. Okay, so first one is the harmonic series. It turns out this one diverges to plus infinity. So, that's from graphically we had this picture, you can prove that it diverges to plus infinity. This 1 by n squared series is really interesting. It has a limit, and the limit is pi squared by 6. It evaluates to 1.6449 something. Okay, pi squared by 6. Notice where pi comes from. Right? It's amazing how pi shows up in these kind of things. The alternating harmonic series 1 minus half plus 1 by 3 minus 1 by 4, again very interesting. It converges to one number which is popularly called ln 2. Ln 2, the natural logarithm of 2, 0.693 something. So, that's what this series is. Okay, We'll see what all these things are. Later on in this course, we'll see all these things, what these things are. This lecture is just to introduce you to what all can happen, what all fantastic things can happen when you study series. Finally, the Madhava-Leibniz series. Why did I call it pi by 4? Because this series converges to pi by 4. Okay, as in this limit of this series is pi by 4, which is 0.785, etc. So this is in fact, the way Madhava studied it back in the 14th century was to introduce this as a way to calculate pi. Okay, so in many problems we may have to calculate pi. So this is how it was introduced. It's called the Madhava-Leibniz series, and it converges to pi by 4. So once again, we haven't seen techniques to compute these things yet. But notice what's happening with sequences and series here. It's a fantastic computational tool. How to compute pi, how to compute root 2, how to compute various different functions of various different types, how to evaluate them, you can do it through series. Okay, so this is a very important and powerful reason for why sequences and series have to be studied, and in particular, how to evaluate limits for sequences and series. We've seen for 1 or 2 sequences, the epsilon proof is okay, but that epsilon proof is a really painful way of going about it. How do I evaluate the limits of sequences and series? Okay, so it's very, very important. We will see simple direct techniques in the ensuing lectures, but hopefully I've shown you enough examples and variety to make you appreciate why we should study sequences and series. In particular, it's useful for function evaluation. We've already seen that, but even for the other problems, how to define continuity, how to think of smoothness, how to think of derivatives and growth and fall and min and max, for all of that also, the sequences are very, very useful. Okay, hope that was interesting to you. Thank you very much.